Sections 5, 6, and 5, 7 have a combined homework assignment to where it's just one homework assignment that covers both of them. But I wrote these up separately. It was kind of easier for me to do it that way. And this way it's two smaller videos instead of one giant one. Now, for both sections, they're mostly about word problems, although there is one new thing that does show up at the beginning of 5.7. So mostly, though, word problems. And so I guess since 5.6 is in front of 5.7, they're going to be word problems that would utilize things that would have just happened recently. So, for example, this first one involves section 5.4. So in 5.4, that was about solving rational equations. That's basically what you do here. So what you would do to solve this thing, so 1 over f equals 1 over p plus 1 over q, it's basically the same as, if I can write way up in the corner here, if you had to solve something like this. So I'm just going to replace the f and the q with some numbers. So what if you had to solve that? Then the first thing that you'd probably want to do is to clear those denominators out. So you get the least common denominator, and then you'd multiply both sides by that. And then you'd end up with probably a linear equation, it looks like, to solve that wouldn't be too bad. And that's what we're going to do here. It's just that now we have more variables, but there's only one that we're interested in. We're going to solve for p. So while we're solving this, we're going to treat the f and the q like they're constants. But then that would mean that the least common denominator would be f times p times q, right? There doesn't look like there's any common factor there. So we're going to multiply both sides by fpq. So that's what I'm going to do here. So I'll have fpq times 1 over f equals fpq times 1 over p plus 1 over q. And then I suppose we could distribute the fpq and I guess multiply it through. So multiply that by the ones in the numerators. So then on the left side we would have fpq over f. And then on the right side, fpq times 1 over p would really just be fpq over p. And then fpq times 1 over q would be fpq over q. And then we can cancel some stuff, or you could just view it as though it's dividing out, to where on the left side, those f's are going to divide out, and you'd have p times q. Then on the right, that first term, you'd have f times q, since the p's are going to divide out. And then on the second one, the q's are going to divide out, so you'd have f times p. So this is where we are right now. So I guess now I can kind of bring this over and up and recopy it. So we're trying to solve for p. And what I would think you'd want to do here is get everything with a p in it on one side. So I'm going to subtract fp from both sides, and that way I'll have both terms that have a p in them on the left. So I'll have pq minus fp equal to fq. And we want to eventually get the p by itself. And right now it's a common factor of the expression that's on the left. So I'm going to factor the p out. And then I'd be left with q in the first term and f in the second. So p times the quantity q minus f, like that, and still an fq over there. And then if you divide both sides by q minus f, you'll get that p is equal to fq over q minus f. And that is the answer. So it's a little bit different looking because it has all those variables in there, but it's the same kind of strategy that you would use if the f and the q had been numbers, where you still want to clear those denominators out, right? That's generally going to make things easier. That's still the case here. Then if you're going to try to solve for p, you'd want to get every term with a p in it on the same side, which we did by subtracting fp from both sides. And then from there, I guess you can't really combine terms, so to speak. I mean, you end up factoring the p out. That part's a little bit different. But then there's a way where you can isolate p and get it by itself, right? Just like when you're solving for a single variable in any equation, that's what you try to do. So there's still a way to do it. It does look a little bit more involved because there are those extra variables, but it's the same sort of process ultimately that you end up doing. Number two, This also involves a rational expression, so I guess the thing in parentheses kind of gives it away that you use similar triangles. You do, you use two right triangles. And so what you'd end up with here, so let's see, we've got this guy here that's 6 feet tall and his shadow is 2.5 feet long. So we know how tall he is, and the shadow would go along the ground, right? So you could make a triangle out of that, connecting where the top of his head is to where the end of the shadow is. And so then we know that the shadow is 2.5 feet, and we know his height is 6 feet. And then for the tree, and I intentionally kind of picked a tree where it's drawn so angularly that you could actually use the top of the tree to make the triangle. You kind of follow along it like that. And then I guess I need that as well. And then these are going to have to connect. Right, so then the shadow is 25 feet. And we don't know what the height of the tree is. So I think to write it in the green, I got to make that light colored. So I'll just make it white. And so that, I guess you could call it X, or you could call it H for height if you wanted. But the way that you use the similar triangles is then you could say, well, then these angles ought to be the same, right? Because the sun is in the same position, right? Like this is happening simultaneously. So then you could say, well, then the ratio of the tree's height to its shadow would be the ratio of the man's height to his shadow. So that's what we can do here. And we can say that this is essentially how you use the similar triangles here. You could say tree height over tree shadow would be equal to man height over man shadow. But then we're going to have that x over 25 equals 6 over 2.5. And then this actually is not that bad because we don't even have a variable in the denominator, right? So if you want to get x by itself, you just multiply both sides by 25. And that's exactly what we're going to do. So 25 times x over 25 would be equal to 25 times 6 over 2.5. So that is going to just be an x on the left side. And then on the right, 25 times 6 is going to be 150. So you'd get 150 over 2.5. And if it's not obvious what number that is, you could get it to where those are both integers. And you could say, well, then x would be equal to 150 over 2.5 times 2 over 2. Right? When you multiply 2.5 by 2, that's 5, so it would be an integer. You get 300 over 5. And now it's easier to see what number that is, since that's going to end up being 60 feet. And I guess here you might be able to see it without doing all the algebra, because you could say, well, wait a second. The tree's shadow is 10 times as long as the man's shadow, so the tree should be 10 times as tall as the man. That logic does work. I wanted to go through it the more formal way, but if you see it that way, that's right. You know, there's nothing wrong with that. So there's nothing wrong with doing it that way if you can see it, and that's the thing that feels like it's the simpler way to go through it. All right, so now we've got a couple that are a little bit longer, and I tried to get every type in here that would show up in the homework. So there's one about two people working together, and then the last one involves motion, so like speed equals distance over time. But with this one, let's see, we're going to have a bunch of given information, and we'll have to kind of piece some things together here. So it says, working by herself, it takes Molly 4 hours to shovel the driveway and sidewalks after a big snowstorm, and if Jim does it by himself, it takes 6 hours. So if they work together, how long would it take? All right, so what we know so far, we know that for Molly, it's 4 hours to shovel snow. And then for Jim, it's 6 hours to shovel snow. And then the other part would be, what if they work together? We don't know what that is, so I guess we need a variable like an x or a t or something. I'm going to use a t since it's time. So I'm going to say t hours. To shovel snow. All right. So we have to figure out a way somehow to equate these things. It's not set up to do that directly, but what we could do is for any specific amount of time, we could figure out how much Molly would be able to get done, how much Jim would be able to get done, and then from there we should be able to solve for how much they'd be able to do working at the same time. So I guess the most logical amount of time, since everything's given in hours, would be to say, well, what could they do in 1 hour, right? Like that would be 1 unit of time here. So if it takes Molly 4 hours to shovel all the snow, then she could shovel 1/4 of the snow in 1 hour, right? That would be another way of saying the same thing here. So we could say she could shovel 1/4 of the snow. So 1/4 of snow shoveled in 1 hour. And then with the same sort of logic, if it takes Jim 6 hours to shovel all the snow, in 1 hour he would shovel 1/6 of it. So 1/6 of snow shoveled in 1 hour. And then t hours working together, well then in 1 hour they would do 1/t of the snow. So 1/t of the snow shoveled in 1 hour. All right, so there is one assumption built into the next step, which seems really logical. There would be no reason for this not to be the case, which is that if they're shoveling together, they're not shoveling the same spots, right? Because if one of them already shoveled a space, then it's clear, right? I don't need to shovel it again. Hopefully. I guess maybe if the snowstorm is still going, but it does say after a big snowstorm, so I think we can assume that the snowing has stopped. So then that would mean if they're working in separate areas, when they're working together, then you could add together what they could accomplish in 1 hour individually, and that should add up to what they'd be able to do together. So that's what we can do. So what we're going to end up doing is we can have, I guess it would be the part done by Molly in 1 hour plus the part done by Jim in 1 hour would be equal to, I guess, the part done together in 1 hour. Barely got it on the page. All right. So then, all right, well, we know what these are. So this would be 1/4 for Molly plus 1/6 for Jim equals 1/t. And then what we're solving for is t, right? How long would it take them if they're working together? Okay, well, we could get the least common denominator here, right? So our denominators, so if we're going to get that, let's see. So 4 is 2 times 2, right? And then 6 is 2 times 3. So what it looks like then, and then I guess t is just t, right? So our least common denominator, we would need a 2 squared, because that's in the 4, and we also need a 3, because that's a factor of 6, times t. So 2 squared times 3 times t, that's 12t. You could just use a common denominator of 24t, which is not the least common denominator. It would still work. You would just have more simplification to do later. So we're going to multiply both sides by 12t. So we'll have 12t times 1/4 plus 1/6 equals 12t times 1/t. And then, let's see, I guess we got to distribute that 12t. So we'd end up with 12t/4 plus 12t/6 when you distribute on the left side. Then that'll be equal to 12t/t. So then we'll get some things to divide out. Since 12/4 is 3, and then 12/6 is 2, we can say, well, then we've got 3t plus 2t equals 12, right? But then you can combine on the left and say that then that's 5t. So then it looks like if you divide both sides by 5, t is 12/5, which it looks like the homework wants these written as decimals. So 2.4 hours. Looks like that would be the way that the homework would want the answer. Because that I actually checked on, because I thought, well, are they going to want it as a decimal, or they want it as like 2 hours and then 24 minutes? Right? Like that would be another way that you could say that, but it looks like just the decimal is fine. So 2.4 hours. And that is what you want here. I mean, that's how long it would take them if they're working together. Right? So way faster than either one of them working individually. But that's because you got two humans working at the same time, right? So that should be faster. All right, number 4, which is the motion or speed one. All right, so what we've got here is a child and a dog raced across a field. Dog ran 18 feet per second, child ran 10 feet per second. All right, so let's see what we're being given here, right? Like this is a speed, right? And then so is this. And then the time is in here. The dog reached the other end of the field 4 seconds before the child. So we don't know any specific times, but basically we're going to have one of them being an unknown and the other one being either that +4 or that -4, depending on how you set it up. So either you'd have a t with a t +4 or a t with a t -4. And then find the length, which would be the distance, right? So usually this is the thing right here that we would think of as being the distance. So if we make a little table here, and I guess we'll have speed, distance, and time. Since the thing that we're using, and I'll put this in like a thought bubble in a different color, just judging by what we're being given, the formula that relates these things together is that speed equals distance over time. So that's what we're using here, right? So I'm just going to put this in like a cloud, like it's a thought bubble, like, all right, this is what we're kind of plotting, that we're going to have to use that formula. All right, and then to finish out my table over here, I guess I need the rows. So then I'd have a row for child and a row for dog. Right, so child, dog. All right, so the child's speed was 10 feet per second. The dog's was 18. And then it said for the time, the dog reached the other end of the field 4 seconds before the child. So either you could say if the child's time is t, then the dog's should be t -4, right? 4 seconds less would be t -4. The other way you could phrase this, if you said the dog's time was t, and then the child's time was t +4, this would still end up working out correctly. So that's okay. And then the other thing is, we don't know what the distance is, but we do know that it's the same because they're running across the same field. So the amount of ground they cover should be identical. So we don't know what the distance is, but it's the same. So if that distance is d, this distance is also d. Okay, so I think we're just about set up. However, it'll be a little bit easier because you can see what we're going to do. We have two different ways that we'd be able to write d, right? Because if you solve for distance instead of having it solve for speed, then you'd be able to express d using the stuff that's in the child row, and you could also express it using the stuff that's in the dog row. And that's basically what we're going to do. So if speed equals distance over time, which it does, so first I'm just going to manipulate the formula. So speed equals distance over time. Then if you multiply both sides by time, because I'm trying to solve for distance here, right? So I'm going to clear that denominator. So time times speed equals time times distance over time, right? So what I'm going to end up with is that distance is equal to speed times time, or time times speed if you want to write it in the same order that it is up there. It doesn't really make much of a difference, but that's what we're going to use. So then we can do this for the child and we can do it for the dog, right? So let's see, then for the child, then the distance would have to be equal to 10 times t. But then for the dog, we would have the distance equals 18 times the quantity t minus 4. But those distances are the same since they ran across the same field, so we can set those equal to each other. And we can say, well then 10t would have to be equal to 18 times the quantity t minus 4. And this looks like it won't be too bad to solve, right? You distribute the 18, and then it's just a regular old linear equation. So we'll have 10t on the left, distribute the 18 on the right, so we'll have 18t minus 72. And then from there to solve it, it looks like we should get 9. So if we subtract 18t, both sides, yeah, we're going to get negative 8t equals negative 72. And then if you divide both sides by negative 8, so negative 8t over negative 8 equals negative 72 over negative 8, then yeah, we're going to get that t equals 9. But we weren't asked about t. We were asked about what the distance is. All right, well then you can just sub this back into either of the equations that are solved for d, either the child one or the dog one. So that first thing that's in blue on the screen right now, the child one looks easier to me. So let's do that. So if d equals 10t, then if you just sub in the 9 for the t, you have 10 times 9, so d is equal to, I lost the ability to write, 90. So d equals 90 feet. And that is the answer. And this also would have worked if you used the other representation of the distance, if you used the dog one. So if you use that, so like just for completeness' sake, I'll stick this in at the end. You'd have 18 times t minus 4. Then you'd be subbing the 9 in for t here. So you get that d is 18 times 9 minus 4, which would mean that d is 18 times 5, but that is 90. So you'll get the same thing. So see, you could have subbed into either one. So the solving is not too bad, and that's what most of these are like. The solving is not actually the hard part. The hard part is getting to where you've got the 10t equals 18 times the quantity t minus 4. So just like when we had these before, these motion problems, because I know it's been kind of a while since we had them, and they were set up before so that you would solve for different things, right? Like you'd solve for different quantities in there so you wouldn't end up with a rational expression. But now we can have that, and you know, here, I mean, we would have it if this was kind of oriented differently, I suppose. But solving for d, that's, I mean, you have to clear that denominator out, right? That's the thing that you do with rational expressions. But even like number 3, like the solving really is not that bad, right? Like 3t plus 2t equals 12. But number 3, the setup is tough, right? So the working together ones, you basically want to see if there's a way where you can set it up so that the amount of time is consistent all the way through. And then there's a way that you can equate things together. Right, so how we kind of rephrased everything so it was in terms of 1 hour. And then that way we could equate them together. That's probably the way to go with something like that. And then, let's see, this one, the similar triangles, that one's usually pretty easy to pick up on. That's what you're going to have to do. And usually the algebra there is really fast, like it is here. But the work ones and the motion ones, when they show up, I think kind of the way that I've got these set up, it's likely to be pretty similar. So whatever you get in the homework is likely to be pretty similar to